Hi, I'm Dr. De Bruin, and this is a quick walkthrough of how to answer an exam question from the bonding topic of AQA A Chemistry. Xenon tetrafluoride is a solid at room temperature, while methanol is a liquid. Explain why these substances have different states. Refer to how the intermolecular forces of each substance arise. Okay, so in this question, they haven't asked me for the shape of the molecule, they haven't asked me for a diagram, but actually I find that that's going to help me to get my thinking together. So here is xenon tetrafluoride. And so you can see I've got 4 covalent bonds between fluorine, which is very electronegative, and xenon, which has about the same electronegativity as carbon. So those individual bonds are polar. So I can add in some little delta negatives for each of the fluorines here and my delta positive for xenon. And so you can see from this what I've got is a symmetrical molecule. So even though my individual bonds are polar, the molecule itself is not a polar molecule. Essentially, I've got a region of negativity around the outside of the molecule and a region of positivity inside the molecule. So I'm not going to have permanent dipole interactions because there isn't one side of the molecule that is positive. The positivity is in the middle. So instead, we're just going to have these very weak van der Waals forces. Now, they've asked me about how these arise. So basically what happens is that there's random movement of the electrons around the molecule, and so at any one time, temporarily, you have slightly more electrons on one side of the molecule. So that leads to a temporary dipole in that molecule. And then that temporary dipole is going to induce a dipole in a neighbouring molecule. And then those two temporary dipoles are going to be attracted together. So that's what's causing my van der Waals forces. Now, meanwhile, I've got my methanol. So again, I've drawn it out just so I can kind of get a clear idea of what's going on here. And as we know, there's a huge difference in electronegativity between oxygen and hydrogen. So that's going to lead to an extremely polar bond. So again, we can show this with our delta positive and our delta negative. So if we go on and we add another molecule of methanol, then you can see here that this hydrogen bond is forming between the delta negative oxygen of one methanol molecule and the delta positive hydrogen of another methanol molecule. And just as an aside, you can see here that we've drawn them all in one straight line, so oxygen to oxygen, all in one line. But that's not the whole story, because we've said in the question that xenon tetrafluoride is a solid at room temperature and methanol is a liquid. So this tells me that the melting point of xenon tetrafluoride must be higher than the melting point of methanol. So there's got to be more here than just the type of weak intermolecular force. We also need to think about the size of these molecules. So xenon tetrafluoride is quite a large molecule. It's got a relative formula mass of over 200 and it's got 90 electrons. So therefore it's comparatively likely that at any one time slightly more of those electrons will end up on one side of the molecule, causing this van der Waals force to arise by induction. And so actually the van der Waals forces that xenon tetrafluoride has are pretty strong. So a lot of van der Waals forces are there and they need a lot of energy to overcome, whereas my methanol is a smaller molecule. So therefore we can conclude by saying that xenon tetrafluoride has a higher melting point because the large van der Waals forces are stronger than the hydrogen bonds between methanol. Thank you very much for watching, and I hope you're finding these walkthroughs of exam questions useful as you prepare for your A-level exams. If you are finding the videos useful, then don't forget to like, subscribe, comment and share for more A-level chemistry resources coming soon.